Hello there, year 9 and 10, and any other years who have decided to attempt the physics mock. Welcome back for another online lesson with St Leonard's Academy Science Department, in particular physics with me, Mr. Devlin. So we don't have any new lesson content, no new lesson content at all this lesson. We're just going to go through the mock that you guys did last week. So I've marked almost all of the submissions, and very, very well done. Some extremely high marks. So congratulations to everyone who completed it. I think if you've been doing the lessons the whole time, all the way through, or even if you've dropped them for a little bit and picked them up again, you can give yourself some real congratulations, because it's going to put you in a really good stead come September. You'll be far ahead of any students who didn't manage to keep on top of their work in the way that you guys have done. So once again, very well done to those who made it all the way through, completed the mock, and many of you, or you've all done very, very well. But some of you have done very, very well. So again, well done. Before I get started, I'm going to try and go through the paper in double quick time. I'm just going to go through it very fast, because you can always stop it and just correct it when I go through. Okay, once I've gone through it. But just before we do so, I have to say that unfortunately, I'm not going to be staying at the academy next year in September. I'm moving on to broaden my teaching experience at another local academy. I've seen the new incoming science team, the new incoming science teachers, and I think it's going to be a very, very strong department going forward. So I really feel like you're going to be in very good hands, which makes me feel happier about moving on and leaving you. To those who I have taught, I'm going to miss you all a huge amount. It's a really tough decision to decide to leave. The thing I'm going to miss most about St Leonard's Academy is you guys, the students. So before I get all teary, I'm just going to press on now and move straight on in double quick time, if I can. I know I tend to drag on a little bit, but in double quick time with marking our physics paper 1 mock. Okay, let's move on. So name, you all got that. Mr. Oh, come on, don't break down now. This will be terribly embarrassing if it's this slow right at the start. Mr. D.P. Devlin. I'll make sure it's nice with capitals in the right place, etc. So that the examiner thinks that I'm smart. Okay, so figure 3 shows the structure of an oxygen-14 atom. Now, oxygen-14 is an isotope of oxygen. Normal oxygens have 16, a mass number of 16. So if we've got an oxygen with a mass number of 14, we know that the number of protons can't change, otherwise it wouldn't be an oxygen. So it must be the number of neutrons which change from a normal oxygen. Oxygen has 8 protons normally, so it must have less neutrons if it's gone down to 14 from 16. So we've got 8, 1, 2, 3, 4, 5, 6, 7, 8. The grey ones, there's 8 of them. So these are our protons. Protons, or proton, which means the other thing in the nucleus. Sorry, I should have explained it. We've got things in the middle, that's our nucleus. Then we've got the electrons around the outside. In the nucleus, we have the protons. If you got these the other way around, I still gave you the mark, because we didn't actually get onto isotopes in the online lessons. They were in the normal lessons, but we didn't get onto them in the online lessons. Around the outside of our atom, we have the electrons, which orbit around. And in the middle of our atom, where we have the protons and neutrons, we have the nucleus. Nuke, N-U-C-L-E-U-S, nucleus. Which of them has a negative charge? That is, of course, the electron. And what's the overall charge of an oxygen atom? It is, of course, the overall charge of any atom is 0. If an atom loses or gains electrons and has a charge, it's no longer called an atom. It will then be called an ion. Okay, so we've got 6 out of 6. Well done me. Let's move on. Some students investigate the speed of cars. They take the time it takes each car to travel a distance of 80 meters. State 2 measuring instruments the students should use. Some of you put a speedometer or radar. Okay, you don't need to go that advanced. In fact, you lose the marks if you go that advanced. It says they measure the time it takes each car to travel a distance of 80 meters. We're going to need something to measure time, and we're going to need something to measure distance. So something to measure time, a stopwatch. Nothing fancier than that. Although if you put a clock, you didn't get the mark. A stopwatch gets you the mark. It's not allowing me to do a comment. Sorry, technical difficulties. Okay, so stopwatch, and then we need to measure a distance. So what do we use to measure distance? We could have a measuring tape, a meter rule, or a measuring tape, meter rule, tape measure. Any reasonable answer like that would do. Got the mark. Okay, and for the next question then, part 2, the table shows some of their results. State the colour of the slowest car. Now they all travelled 80 meters. Speed equals distance over time. The lowest speed will be the one with the largest time because time is under speed. And that makes sense. If something takes a long time to travel a distance, it's going to be very slow. In this case, the car that travels the slowest is the one with the longest time, 5.6, is going to be the white car. White car. Calculate the speed of the black car. Most of you got this, almost all of you got this. I was very pleased to see because I sang not so stupid songs and played the stupid songs. Speed equals distance over time. Speed equals distance over time. We have a, no, I want that bigger. Write out the equation. Always speed equals distance over time. Distance is 80 meters divided by the time. The black car is 4.3 seconds. 80 divided by 4.3. Put it into your calculator. Clear. 80 divided by 4.3 is equal to 18.6. 18.6, and the unit they've given it to you is meters per second. 18.6 meters per second. Now there were a whole bunch of other numbers, but they're not important because we have each of these is only to 1 or 2 significant figures. So I've put it to 3 significant figures just to be sure, but I don't need any more significant figures than that. I don't need any more precision than that. Okay, next one. I need to see both of these on at the same time. 20 miles an hour is approximately 9. Estimate the speed in miles per hour of the black car. They're indicating the black car. Okay, we've calculated it as 18.6 meters per second. And they say in part 3, 9 meters per second. Think to yourself, how do I relate those? They've asked for an estimation. 9 meters per second is approximately half 18 meters per second. So if 20 miles per hour is approximately 9 meters per second, 18 meters per second, being double, is probably double 20 miles per hour. And indeed, the answer is 40 miles per hour. 40 miles per hour. If you calculated it to greater precision than that, you still got the mark, but 40 is what they're really after. They're just looking for an estimate. Okay, a car. Next one, question 3. A car with mass 1,800 kilograms is accelerating at 1.2 meters per second. Calculate the force used to accelerate the car. Use the equation force equals mass times acceleration. F equals m times a. Force equals mass times acceleration. Force equals 1,800. That's our mass. Multiplied by the acceleration, 1.2. Type that into your calculator, and you get 2,160. If my memory serves, I'm not a genius. I've just been doing this already. 2,160 newtons Now, you guys, of course, would write that answer in the proper place. For the interest of speed, I'm going to just forge on so we're not here all day. Many of you got that last one right. Many of you also got this one right. It's a little bit more complicated because it had a square in it, but not much. Okay, they've given us the equation. A model train has a mass of this. It travels at a speed of this. Calculate the kinetic energy using this equation. Kinetic energy equals half times mass times speed squared. No rearrangement needed. Kinetic energy equals half. I'm going to write 0.5 for half times by mass. The mass is 8 kilograms times by the speed, which is 1.5 meters per second squared. I've written squared like that because I'm on Adobe, so it's difficult to write superscript. Okay, you've got a mark. We can start calculating this already. 0.5 times 8 is the same as half of 8. Half of 8 is 4. 4 multiplied by 1.5 squared. 1.5 squared is the same as 1.5 times 1.5, which is equal to, so you can write 1.5 times 1.5. It's 1.5 squared, which I don't need to calculate it because I've done it already, is 4 times by 2.25. 4 times 2.25 is equal to 9 joules. There we go, boom, that's our 3 marks. You get a mark for putting the numbers in, substitution. You get a mark for correctly calculating the square, and you get a mark for the right answer. Always, always, always write out your writing. Okay, if you got 3 marks. However, if you got one little bit wrong, one little bit of your calculation wrong, you wouldn't get those marks. You would get none if you just wrote the answer and your answer was wrong. Slight technical difficulties. Come on, computer. Here we go. Question 5. Figure 2 shows an energy transfer diagram, also known as a Sankey diagram, for a steam engine. The diagram shows the amounts of energy transferred each second by the steam engine. We've got 2,000 joules going in each second. We've got 160 joules of useful energy coming out, so that'll be like kinetic energy, because that's what we want. And we have an amount of wasted energy. Think back to the law of conservation of energy. Energy cannot be created or destroyed, only changed in form. That tells us whatever goes in must come out. The energy input must be equal to both the energy output. So the wasted energy is going to be equal to the energy input minus the useful energy output. Calculate the amount of wasted energy. It was great to see most of you, almost all of you, got this one right. So it's going to be energy input minus useful energy output. 2,000 minus 160, which will be 1,840 joules. I'm not going to put that in the right place, again, to save time. We just need to know this has got to equal these. Okay, now they've given us an equation here, and we just need to put in the right answers. We just need to put in the right values. Efficiency is equal to the useful energy transferred by the steam engine divided by the total energy supplied to the steam engine. They want us to calculate the efficiency. The useful energy is here, 160. The total energy supplied is the same as the input, is 2,000 joules. So our efficiency is going to be, efficiency is equal to 160 divided by 2,000. That's all. You got a mark for that, and then you got a mark for calculating it. I happen to know it is equal to 0.08. That's the correct answer. Some of you wrote 8%. Very well done. Efficiency is often shown as a percentage. To change the 0.08 into a percentage, multiply by 100, and you'll get it as 8%. So either 0.08 or 8% was the correct answer. So what happens to the wasted energy? There are lots of different answers you could have used for this one and still got the mark. So changed to another form, got you the mark. Lost to the surroundings. If you wanted to be really fancy, you could have written dissipates to the surroundings. Transferred or lost as heat. Heat or thermal energy. Got you that, Mark. Okay, there we go. Coal is a fossil fuel that's burnt in some steam engines. State 2 ways coal might be harmful to the environment. Now you had to be a little bit specific here. Okay, you couldn't just write pollution, although air pollution would have got you the mark. But let's think, what does coal specifically release? So burning coal releases carbon dioxide, which causes global warming. One answer. Make that smaller. And coal particularly also releases, burning coal releases sulfur dioxide, which causes acid rain. Other answers you could have had there are that coal releases soot, which can damage buildings. Could also be coal, the mining of coal damages the environment where it's mined. Could also say releases carbon monoxide. Are other potential answers. Okay, this one's tough. Some of you got it right. Very well done to those who did, but many of you didn't get it right or didn't even attempt it. Of those who did get it right, a lot of you wrote out the numbers in standard form in a normal form and then simply did the calculation. So very well done if you did that. It's very labor intensive. There is an easier way. It might not seem easier, but I promise you it is easier once we get used to it, okay? So the first thing we had to realize, okay, we've got two masses. Mass of a proton is this, mass of an electron is this. How many times the mass of a proton is greater than the mass of an electron? So I want to know how many masses of an electron fit into the one mass of a proton. So I'm going to divide mass of a proton, the bigger one, divided by the mass of the electron. Many of you did a subtraction there, okay? The first thing to realize is that it's a divide, okay? So then we're going to do 1.6726 multiplied by 10 to the power minus 27 divided by 9.1, I'll put it in brackets, 9.1094 multiplied by 10 to the power minus 31. Okay, the first thing to realize when we're multiplying or dividing numbers in standard form is that we can split up our division or our multiplication into two parts. We can divide, so in this case, we can divide the number, so the 1.6726, we can divide that by 9.104. And then we can multiply that answer by 10 to the power minus 27 divided by 10 to the power minus 31, which is going to look something like this. I'm going to see if I can draw this out properly. So 1.6726 is going to be over. I want it to be over the top of. I can't draw a line there. Okay, I'm going to have to do it all in one box. Let's expand this down. Let's get rid of that. Okay, it's going to be a bit confusing because I can't draw this out as I'd like, but it's going to be 1.6726 divided by 9.1094 multiplied by 10 to the power minus 27 divided by 10 to the power minus 31. Okay, so I've split my division up into two parts. I'm dividing this by this, and I'm dividing this by this. Okay, 1.6726 divided by 9.1094. Let's do that on the calculator. It is going to be, I've done it here before, 1.6726 divided by 9.1094 is going to be equal to, where was it? It's this one here, 0.1836. I'm only going to go to 4 significant figures to keep it simple. It's going to be 0.1836 multiplied by, and here we can use a trick for factors of 10. If we have two factors of 10 divided by one another, we can, using the rule of orders of magnitude, we can simply subtract them from each other. So if I have 10 to the power minus 27 divided by 10 to the power minus 31, it is equal to 10 to the power minus 27 minus 31, because it's minus 31. 10 to the power minus 27 divided by 10 to the power minus 31 is the same as 10 to the power minus 27 subtract minus 31. Now those of you who are good at maths will know that if we minus a minus, it becomes a plus. Okay, so we're going to have 0.1836 multiplied by, open brackets, 10 to the power minus 27 plus 31. Minus 27 plus 31 is going to be 4. So it's going to be 0.1836 multiplied by 10 to the power 4. Now to convert this into a normal number, 10 to the power 4, that should be a point. If it's times 10 to the power 4, we move the decimal point 4 places to the right. It's going to be 1,000, which will jump it 1, 2, 3, 4 to just the other side of the 6. It's going to be 1836 times. So an electron is 1,836 times less massive than a proton. Now look very closely, because they've asked us to two significant figures. That's the two numbers to the left, furthest to the left. It's going to be 1,800. After the 8, there is a 3 that is below 5, and so we round. We keep it at 1,800. If it was above 5, it'd be 1,900. So to two significant figures, that's our answer. 1,800 times. Boom. Apologies if I made a bit of a meal of that. I'm not that great at maths because I don't teach, or teaching maths anyway, because I don't teach it as much as I should do. Okay, let's move on. Finally, almost finally, question 7. The electromagnetic spectrum has many parts. One of these is called visible light. How many different colours are there in visible light? Put a cross in the box next to your answer. Remember, Richard of York gave battle in vain, or Roy G. Biv, all the colours of the rainbow. Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. Roy G. Biv, there are 7. Which one of those has Complete the sentence by putting a cross in the box next to your answer. 3 colours of the spectrum of visible light in the correct order are green, red, yellow. No, I don't think so. Write it out if you don't know. Roy, G, Biv, orange, yellow, green, blue, go violet, Roy, red, orange, yellow. There we go. And which part of the electromagnetic spectrum is used for what use? Ultraviolet. Magnetic. 7C part 1. We've got 2 images of a hand. One is an infrared image and one is an X-ray image. What information does the infrared image give us about the hand? So the 2 marks you've got here are that we can see areas of different intensity, which indicate, that's in the black and the white patches, the darker and the lighter colours, which indicate temperature. Let's make that big. So areas of different colour / intensity on the infrared image indicate different temperatures. And then think what different temperatures might be on a hand. On a hand, I'd say it's probably something to do with blood flow, could be. On a hand, the higher temperatures could be due to larger amounts of blood flow. Or you could write where the veins are, where greater blood flow is, where the arteries are, for example. I've misspelled some of these, but oh well. Okay, part 2, explain why taking an X-ray image and an infrared image. Again, 2 marks, so we need 2 different things. So X-rays have a higher frequency than infrared radiation. Think where they are on the infrared, on the electromagnetic spectrum, than infrared radiation. They also have more energy than infrared radiation. Okay, so that's telling us why they might be more dangerous. When X-rays pass through or penetrate our hand, they can damage our cells / DNA, potentially causing cancer. That's why X-rays are dangerous. So we've got a bit overkill there, probably got about 3 marks out of 2, but it's good to just include a few extra. The critical things are I need to say how X-rays are different from infrared radiation. They have a higher frequency, a higher energy. When X-rays penetrate our hand, they can damage our cells or DNA, potentially causing cancer. How do they give us that damage? There we go. Okay, last one. Very well done if you've made it this far. Question 8. Explain the differences between longitudinal and transverse waves. And your explanation should refer to ultraviolet, ultrasound, and seismic waves. If you did not include ultraviolet or ultrasound or seismic, you could not get all the marks. They've told you have to include them in the answer, okay? And then the other thing quite a few people got wrong is they wrote that for longitudinal, the particles or the wave travels parallel to the direction of wave travel. And that could mean that the particles are moving in one direction from one place to another, whereas in fact they are vibrating or oscillating about one position. So we need to write that in a longitudinal or transverse wave, the particles vibrate or oscillate, not that they move, because that seems to say they're moving from one place to another. Okay, so let's get those marks. Longitudinal vibrations / oscillations are parallel to or along or in the same direction as the direction of wave travel or propagation, wave propagation. That'll give you 2 marks already, that you've got vibrations and you've got parallel to the direction of wave travel. Transverse, then, vibrations or oscillations are at right angles to or perpendicular at right angles, is also perfectly right, to the direction of wave. There we go, that's 4 marks. And now we need to explain, we need to give some answers for ultraviolet, ultrasound and seismic. Ultraviolet is part of the electromagnetic spectrum. It's just above visible light, and so it's a transverse wave. Honestly, it's this easy. Ultraviolet is a transverse wave. Ultraviolet waves are transverse. Wave, mark, tick. Ultrasound. So ultrasound are sound waves which are such high frequency that our ears can't pick them up. They're still sound waves, but they're very, very high frequency sound waves. And we know that sound waves are longitudinal waves. So ultrasound waves are longitudinal waves. There we go, tick, 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 tick. That's 6 marks out of 6. Let's just get the rest. Seismic was a tough one, okay? Seismic waves, because they can be either. Seismic waves are both longitudinal and transverse. You can put, to be super fancy, P waves or seismic P waves. P waves are, and I think P waves, I think pressure waves. Sound is a pressure wave, and I know that that's longitudinal. So seismic P waves are longitudinal. And seismic S waves, and I think of an S and I think of it as a kind of transverse kind of S-y shape. Seismic S waves are transverse. S transverse. There's no S in longitudinal. So S waves are transverse. Boom, there we go, 6 out of 6. And that is how to get 100%. So we are at the end of our paper. Thank you very much to those who have followed along the whole time, and to those who have done the test and submitted it. If you've done the test and just marked it at home, that's also absolutely fine. This is the last you'll see from me. So all the best, as I've already said, all the best of luck in the future. I'll miss you. See you around the way.